Is it a bird? Is it a plane?
Nope. It's today's challenge.
Oh, cool.
Go on then, open it.
Rearrange formulae to prove that flying is safe. You know I hate flying.
Oh, don't be such a baby. Statistically, flying's much safer than driving.
Yes, and statistically, I panic more during takeoff and landing than I do driving down the motorway. So what are you going to do about that?
Well, like I said, what we're going to do is rearrange different formulae, and by doing that, I'm going to show you just how safe it is to fly. There you go.
I'm not flying it as well.
No way. But, could you take some timings for me? Rearranging formulae means making one letter the subject. Now, I'm going to explain this using a chicken. Yep, a chicken. Hello. Now, when you buy a chicken, they often have cooking instructions on them, and they read a bit like this. Cook the chicken for 45 minutes for every kilogram and add 30 minutes. Thank you. Now, if we wrote that as a formula, it would look like this. T equals 45W plus 30, where T is the cooking time in minutes and W is the weight of the chicken in kilograms. But what if we only had a limited amount of time to cook our chicken, let's say 2 hours, and we wanted to know the largest chicken we could cook in that time? Well, we could solve that one numerically, like an equation. 2 hours is 120 minutes. So that means that T equals 120. And that means our equation now becomes 120 equals 45W plus 30. But to find W, we need to get W on one side of the equation and all the numbers on the other. So let's start by taking the 30 away from both sides. And if we simplify, that gives us 90 equals 45W. And let's divide both sides by 45. And that gives us W equals 2 kilograms. But what if we want to find the weight for lots and lots of different times? Well, we need to find one formula where W is the subject. So we need an equation that starts W equals. And we can get that by rearranging our original formula, T equals 45W plus 30. So let's follow exactly the same steps as we just did. So subtract 30 from both sides and simplify. That gives us T minus 30 equals 45W. And divide by 45 to get W by itself. And that gives us T minus 30 divided by 45 equals W, which, if we switch it round, it's exactly the same as W equals T minus 30 divided by 45. So now all we've got to do is substitute in different values of T, and that will get us the weight. So now we know about rearranging formulae, how are we going to use that knowledge to help Dave feel more comfortable about flying? Well, I know that Dave is most scared of takeoff and landing because he doesn't actually think the runway is long enough for either. And I'm going to show him that there is plenty of runway for both the takeoff and the landing by using different formulae. The first one I'm going to use is this, V equals U plus AT, which is velocity equals starting speed plus acceleration times time. But first, I'm going to need a few figures from the airfield.
So I'm here at Stapleford Aerodrome having my 10th cup of coffee for the morning. I hate flying. Although if we find out something about maths, then I guess it's worth it. Although what flying has to do with formula, I have no idea. Aha, my instructions. I'm going to prove to you that takeoff and landing is safe. To do that, I will be using different formulae and I need you to take some information for me. That sounds pretty straightforward. Aha, and here's what she wants. The taxiing speed of the aeroplane before it starts accelerating for takeoff. So that's the bit when we're driving along to get to the runway. Fine. The speed the aeroplane is going when it does take off, so that's when the wheels leave the ground. I'll probably be passed out by that point. And the time it takes to go from taxiing to takeoff. That's what the stopwatch is for. Good luck, go and find yourself a friendly pilot and send me through the data when you have it. Just need a pilot.
I'm going to use V equals U plus AT to find out how fast a plane needs to accelerate to take off. where V is the takeoff speed, U is the taxiing speed, T is the time to take off, and I've got to get A as the subject of the formula. And how do I do that? Let's do it in the same way as we did for the chicken cooking formula. So we want A as the subject, so let's take U away from both sides, and these U's will cancel out. So let's divide both sides by T, and then these T's cancel out, and let's swap that around, and that gives us A equals B minus U divided by T. Now to use this, I'm going to use some figures from Dave. Where are they?
So I've managed to find a pilot who has a plane and he's going to take off so we can do some timings, and I'll be able to hear him over this. So here we go.
As I taxi to the runway, maintain 10 miles an hour, safe taxiing speed.
Okay, so he's taxiing at 10 miles per hour. I need to keep an eye on that speed because that's going to be our U in the formula, which is our starting speed. As soon as he starts to speed up for takeoff, I'll start timing.
Lined up on the runway now, opening the throttle.
And there he goes. As soon as his wheels leave the ground, that's when I'll stop timing, and that'll be our T in the formula.
Rotate into flight.
There we go. So that's 20 seconds from when he started to when he took off. And I'll just get his speed.
70 miles an hour.
That's 70 miles an hour. I'll just go and tell Fran.
So here are the figures from Dave. Now, first of all, I'm going to convert these values into meters and seconds, and that makes the numbers a little easier to work with. And here's how we do it. Let's convert 70 miles an hour using an approximate conversion of 1 mile equals 1.6 kilometers. So if we times by 1.6, that means we get kilometers per hour. So 70 times 1.6 gives us 112 kilometers per hour. And we know that there are 1,000 meters in 1 kilometer. So multiplying by 1,000 gives meters per hour. So 112 times by 1,000 is 112,000. Now let's convert the time to seconds. And we know that there are 3,600 seconds in 1 hour. So if we divide by 3,600, we get meters per second. So that means 112,000 divided by 3,600 gives us approximately 31.1 meters per second. And that means 70 miles an hour is about 31.1 meters per second. And if you do exactly the same working, you can find out that 10 miles an hour is approximately 4.4 meters per second. So all of this means B equals 31.1, U equals 4.4, and T is the same as it was, 20 seconds. So let's feed those figures into our rearranged formula, A equals V minus U over T, and that gives us A equals 31.1 minus 4.4 all over 20, which gives us A equals 1.335 meters per second squared. Right, now we know the acceleration the plane needs to take off. We can work out how much runway it needs to take off using a different formula. This one, S equals UT plus half AT squared, where S is the distance. Now it's easy to think that S is the speed, but it's not. Remember that S is the distance. So let's put all of those figures in and we get a distance of, you ready for it? 4.4 times 20 plus half times 1.335 times 20 squared, which comes to, thank you computer, 355 meters. So that means that the aeroplane needs 355 meters to take off. Now let's talk to Dave. Hey Dave, how you doing?
Yeah, it's a bit cold, but okay.
I've got a question for you.
Yes.
How long is that runway?
Oh, hold on, I'll inquire. How long's the runway?
1,100 metres.
1,100 metres.
Ah, well, Brill, I've worked out that the aeroplane needs 355 metres, so that's just under a third of the runway for it to be able to take off.
Well, that's a relief, but what about landing? There's no way I'm getting in a plane unless you can tell me the runway's long enough to land on, no matter what speed they're doing.
Well, for me to work that out, I'm going to need a different formula.
But what I need you to do is find out how quickly the plane can slow down compared to how quickly it can speed up. Do you think you can do that?
Yeah, I already know that one. A plane can slow down twice as fast as it can speed up. So it can go from 70 to 0 in about 10 seconds.
Oh, well, that's brilliant. I'll work out the maximum approach speed for that length of runway.
I'd like to show you another formula, this one. v squared equals u squared plus 2as. This motion formula connects final velocity, starting speed, acceleration and distance. Now I want to work out what's the fastest speed the aeroplane can approach the runway and still stop in time. So I want the subject of the formula to be u, which is the speed of the aeroplane when approaching the runway. V, if you remember, is the final velocity, which we really hope is going to be 0, as I guess Dave would like the aeroplane to stop. S is the length of the runway, which we already know, and A, in this case, is the acceleration, but because the plane's decelerating, it's going to be a minus. So let's rearrange this formula so we can get u on one side. So we've got the formula v squared equals u squared plus 2as. So let's start by taking 2as away from both sides. Brilliant, and that cancels out from the u side, which gives us v squared minus 2as equals u squared. Now we just want u by itself instead of squared, so let's square root both sides, and that gives us square root v squared minus 2as equals u, which of course we can just flip round to get u equals square root v squared minus 2as. Now let's put some figures in. We already know that v is 0, and with the information that Dave gave me, I've worked out that the plane's acceleration is minus 3.31, and the length of the runway is 1,100 metres. So let's calculate all that, and we get square root 7,282, which gives us a u of 85.3 metres per second. Now we can convert that to miles an hour, and that is brilliant. Thank you, computer. Just over 190 miles an hour.
Hey Dave, I've got an answer for you. From all the figures that you've given me, so that being the length of the runway and how quickly the plane can slow down, I've worked out that the plane needs to be travelling faster than 190 miles an hour for it to run out of runway. So if you're travelling less than that, then you'll be all right.
Okay. Excuse me. Hi there. Can you tell me what speed does the plane approach a runway at for landing?
Safe approach speed is 70 miles an hour.
Okay,
Come on board, I'll show you.
But you know, they always say check your workings out. Maybe do it 2 or 3 times just to be safe. And I need a calculator. Oh, at least tell me you've got some peanuts on here. Yeah, if you can just double check this as well. I mean, she could have made a mistake. Yeah, I'll just hold on to here tight, a bit tight. Yeah. Do you mind if I sit in the back? And yeah, I guess she was right.